The sanitary arrangements of an early Georgian house were basic. Bathrooms were unheard of. Instead, most houses had a small shed containing a fixed wooden seat with a round hole. This was the privy, although it went by other names such as the necessary or bog house. The seats often contained 2 or more holes graded according to the size of the user. The waste accumulated in a heap under the seat. This was known as a midden and was periodically emptied by nightmen. Commodes, portable seats enclosing a chamber pot, were often used in closets adjacent to bedrooms. By the 1750s, water closets were being introduced into the very best houses. They consisted of a basin or pan which held a reserve of water. They were called valve closets, and the earliest description of one appears in a patent taken out by Alexander Cummings, a London watchmaker, in 1775. Cummings also provided a water-sealed trap to block the passage of sewer gas. To discharge the waste, a handle in the seat was pulled upwards. The valve slid to one side, while another valve simultaneously admitted clean flushing water. Joseph Bramah patented an improved valve closet in 1778, and in 1780 the pan closet appeared. This relied on a tipping pan to discharge the waste. Enclosed in handsome mahogany cabinets, these mechanical closets were expensive and complicated, but by the 1820s were in widespread use in middle-class homes. The increased use of water closets at this time was, however, something of a mixed blessing. The fundamental problem was that water closet technology, whatever its shortcomings, had outstripped that of sewage disposal. The waste from the average early 19th century WC didn't travel far. Many drained into cesspits in the backyards of houses. Some discharged into nearby rivers, and others directly onto the street. At a time when the populations of towns were rapidly expanding, the result was a catastrophic deterioration in the quality of river and well water. A wave of fatal diseases such as cholera and typhoid finally brought the problem to the attention of the government. Surveys carried out in the 1840s under the guidance of the great public health reformer Edwin Chadwick revealed the true scale of the problem. In 1848, the first Public Health Act was passed. Local authorities were empowered to create sanitary authorities. And by the late 1850s, some towns and cities had embarked on massive programmes of sewerage construction. Where sewers were laid, homeowners were compelled to make connections to them. As a consequence, water closets lost their exclusive middle-class image, and for the first time became a standard fitting in areas of working-class housing. However, many northern towns continued to use dry privies, where the waste was neutralised by earth or ash and collected in buckets. The water closet of a working-class home was very different from the expensive mechanical closets used by the rich. They consisted of simple funnels or basins fitted to a water-sealed trap. They were called hopper or cottage closets, and some, like this closet of 1884, had no provision for admitting a flush. They were also usually placed in the backyard. From the 1870s, improved supplies of mains water, better house drainage and improved standards of personal hygiene led to bathrooms being built in middle-class villas. Alongside fitted baths and wash basins with running hot and cold water, the water closet of the 1870s and 1880s rapidly evolved into an all-ceramic water closet without valves. The first pedestal washdown toilet, the Beaufort, was introduced by Frederick Humferson, a London manufacturer, in 1885. The modern water closet had finally arrived. A network of pipes above the ground is required to connect bathrooms and WCs to the underground drainage system. By the end of the Victorian period, the two-pipe system, usually made from cast iron, was the most common method. In a two-pipe system, one pipe collected foul matter from the water closet and another collected waste from the bath and basins in an open hopper head. This hopper also collected rainwater from the guttering. Although both pipes usually ended up in the same sewer, sanitary engineers of the time felt it was prudent to separate foul and waste matter above ground level. Drain smells could not enter the house through the soil pipe because of the trap in the base of the WC. Smells couldn't rise through the waste pipe because it was usually trapped at its base. By 1900, most baths and basins were also trapped. The soil pipe continues up beyond the roof to provide ventilation for the drainage system and keep smells away from the occupants. The kitchen sink waste fed directly into the trapped gully at the foot of the waste pipe. For a trap to work, it has to be full of water. But there are situations where the traps below sanitary fittings can fail. These are caused by pressure variations, which can result in siphonage. Self-siphonage can occur where the waste, say from a basin full of water, runs fast and full bore along the branch pipe, taking the trap water with it. Induced siphonage can occur where water from an upstairs fitting sucks water out of a lower branch pipe. In these early systems, siphonage was prevented by the addition of vent pipes. These extra pipes were expensive, complicated and untidy. Self-sealing traps, patented in the early 1920s, were an alternative solution. However, they were not cheap and could be quite noisy in operation. By the early 1900s, most underground drainage pipes were machine-made from extruded clay. During firing, salt was thrown into the hot kiln to provide a waterproof glaze. Joints could be formed in a number of ways, and manufacturers were keen to promote their latest inventions. A typical joint would contain bitumen or tarred rope sealed with cement mortar. These rigid joints could not tolerate ground movement, so cracks and leaks were common. A variety of bends and fittings were made to suit any drainage layout, however complex. During the 1920s and 30s, millions of private and local authority houses were built on large estates throughout the country. Most of these houses were built with cast iron two-pipe systems which ran into a single combined sewer, usually located in the road. In this 1920s estate, a shallow drain approximately 500 millimetres deep, running along the back of the houses, picks up the foul water from the soil pipes. The branch pipes are swept in the same direction as the fall to help minimise blockage. In other examples, there might be inspection chambers to provide ready access. The rear drain also collects waste and rainwater from a shared waste pipe serving the bathrooms. To reach the sewer, the drain has to turn through 90 degrees and run between the houses. Blockages are always likely to occur at changes of direction, so an inspection chamber has been provided. As the drain runs towards the sewer, it picks up the kitchen waste and the side and front rainwater pipes. The sewer also collects stormwater from the road. The effluent will eventually end up in the local sewage treatment works some 5 miles away. At regular intervals, changes of direction, and when there are branch connections, inspection chambers are provided for quick and easy access. For the last 30 years or so, plastic underground drain pipes have been available, but clay pipes and fittings are still very popular. In modern manufacture, blended clay is broken down by a crusher and is ground to a fine particle size. Water is added to make the mixture workable. The clay is extruded through a die to form a cylindrical pipe. Each batch of pipes is given a unique serial number to aid quality control. Before the clay is fired, it's allowed to dry. During the drying process, the pipes are inspected for flaws. The pipes in this factory are fired in a tunnel kiln where the temperature is raised progressively to 1100 degrees. During firing, vitrification takes place. This is the process which gives the pipes their high density and impervious surface. These pipes, unlike their earlier counterparts, have flexible sleeve joints rather than spigots and sockets. This ensures that minor ground movement doesn't cause leaks. In a modern underground drainage system, there are usually separate pipes for stormwater and foul water. The foul water from WCs, baths and sinks runs to the local sewage treatment works, and will eventually be discharged into streams and rivers. Stormwater from roofs, paths and roads, by its very nature, is clean and can be directed straight into rivers without treatment. This separate system of drainage, unlike the earlier combined system, reduces the load on the sewage works. In addition, there are no peak loads following high rainfall. Above the ground, the soil and waste water is now usually carried in one pipe, called a single stack. Careful design can minimise the risk of siphonage. To this end, the building regulations require minimum trap and pipe sizes and limit the length and fall of branches to ensure that they do not run full bore. If the design parameters can't be met, ventilating pipes or self-sealing traps will have to be introduced. On buildings up to 3 stories high, the stack can be fixed either inside or outside the house. Above this height, the stack must be fixed inside for reasons of frost protection and access. The single stack system can easily be adapted to suit blocks of flats. Here, there are 2 flats on each story. In modern systems, rainwater is not carried in a single stack. Rainwater downpipes take water from the guttering into the stormwater drain and onto the stormwater sewer. The sewer will also collect water from roads and paths. On this housing estate, the underground drainage system is plastic, but whether plastic or clay, the connections to the above-ground drainage will be similar. Let's look at the foul connections first. The soil vent pipe runs into a rest bend. No trap is required because the WC has an integral trap. A downstairs waste pipe, if not connected to the stack, can also run into a rest bend, but if quick access is required, it's better to use a trapped gully. The gully allows external access to clear blockages. The trap prevents smells escaping into the air. The storm connections depend on whether the drainage system is combined or separate. In a separate drainage system, the rainwater pipes can join a drain with a simple rest bend. A rodding eye with a cover plate provides rodding access. A trapped gully is required if the system is combined. This can also collect surface water and provide access to clear blockages. A yard gully must be trapped if it joins a combined system. Even in a separate system, it's normally trapped in case of gases in the storm sewer. The building regulations for drainage are in part quite complex. However, there are some basic principles. Layout should be simple, and pipes should have adequate capacity to carry the flow. Pipes should be laid to even gradients and in straight lines, at least straight enough for rodding. The Pipework should have adequate protection to minimise damage. Access must be provided at regular intervals to clear blockages, and the whole system must be adequately ventilated to prevent the build-up of harmful gases. And of course, the layout must be watertight. On this layout, the main drain isn't straight. The left-hand branch joins the drain against its flow, and the right-hand branch has got a sharp bend in it. The solution is simple. Here the gradient is uneven. These pipes are too near the trees and could be damaged by roots. There's also the risk of fracture where the pipe passes through the external wall. Flexible joints either side of the wall minimise the risk. Another option is to form an opening with a lintel over the top. Pipe trenches are nowadays nearly always excavated by machine, and ensuring the trenches are straight and dug to the right gradient is quite a skilled job. The choice of bedding and backfilling material depends on the depth of the pipes and their size and strength. If the ground is good enough quality, it's possible to trim the trench bottom and lay clay pipes directly onto the surface. The excavated material can be used as backfill. In practice, it's usually cheaper and quicker to provide a gravel bed. The gravel must be free of fine material, or else it will compact and prevent the pipes from moving. Plastic pipes, because they're not as strong as clay ones, always require a gravel bed and surround. Under drives and roads, trenches may have to be backfilled with hardcore. Where they're very shallow, protection can be provided by concrete slabs spanning the trench. Another option is to surround the pipes in concrete, although there must be gaps in the concrete at every pipe joint to allow for minor movement. Access points, usually in the form of inspection chambers, are required at regular intervals to clear blockages by hand or to allow rodding or jetting. They are required near the start of the drain run, at changes in direction or gradient, and where branches meet the main drain. They are also specified at minimum intervals on long runs. Shallow inspection chambers can be made from clay or plastic, usually surrounded by concrete if they are on drives or footpaths. Deeper inspection chambers have to be large enough to climb into and strong enough to resist ground loading. They're usually made from pre-cast concrete rings of various diameters. Open channels at the bottom of the inspection chambers give access to the drain. At the design stage, the architect or engineer will plan the drainage layout, and this will determine the position of all the inspection chambers. A site plan, for example, might show their grid position and invert level. A schedule might specify their cover level, size and construction. The invert levels depend on the required falls. For example, if the invert level of 2 inspection chambers differs by 300 millimetres and they're 30 metres apart, the fall is 1 to 100. Up until the end of the 19th century, raw sewage from the city of Bath was discharged straight into the River Avon. As the population grew, pollution levels in the river rose, until in 1910 work started on building a sewage treatment works at Salford, a few miles from the city centre. Sewage from Bath flows under gravity to a pumping station on the outskirts of the city. From here, it's pumped through a 5-mile pipeline to the treatment works. The pipe can carry up to 25 million litres of sewage a day. As sewage enters the works, it passes through a screen which removes any debris such as rags, paper and plastic. This debris is washed, then shredded and put in a skip ready for licence disposal. After screening, the sewage flows through a tank where any grit can settle to the bottom. Grit has to be removed at this stage to prevent it blocking later processes. The sewage is then fed to primary settlement tanks, each of which is 14 metres deep with a steeply sloping floor. The sewage spends 2 to 6 hours in these tanks, during which time the suspended solids settle to the bottom, forming a sludge. A scum plate is fitted around the edge of each tank to hold back any fat or scum which collects on the surface. Ferric sulfate is added to help settlement and to remove phosphates, which would otherwise encourage algae growth in the river. Phosphates are found in a variety of detergents and other cleaning products. The sludge is removed automatically and treated to turn it into dry, odourless granules, which can be used as a soil conditioner. At Salford, there are 20 biological filter beds. Each one is 30 metres in diameter, 2 metres deep, and contains around 2,000 tonnes of blast furnace slag. This material, with all its pits and fissures, has a large surface area on which bacteria can grow. The bacteria feed on the sewage, helping to purify it. The filter bed is also home to flies, worms and leeches, which eat up the bacterial slime, preventing the filters from clogging up. The sewage is distributed across the bed by a rotating arm, driven by a water wheel which keeps the arm moving at a constant speed. Some rotate due to the jetting action of the water. The final settlement tanks allow any dead bacteria, called humus, in the water to settle, forming a layer of sludge which is removed and treated. The water is now clean and safe enough to be returned to the environment. It's discharged into the River Avon downstream of a weir, the turbulence aerating the water and keeping it fresh.